Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of profsam.com. Today, we're diving deep into a really foundational concept, temperature dependence of resistivity. It's from Unit 3, Current Electricity. Our mission here is simple. We want to break this down so you understand it completely, lose any fear, and can, tackle any exam question with confidence. So let's start with something you see every day. Why does your mobile charger get warm after you've used it for a while? What do you think is happening there?
I think it's because current is flowing, right? And the wire must be resisting that flow, so that opposition generates some heat. Joule heating, I think it's called.
Exactly, that's Joule heating, and it's all tied to resistance. But here's the surprising part, something really counterintuitive. Think about an old incandescent light bulb. When you first flick the switch, the filament inside is cold, and for a split second it draws a massive surge of current. But then, just milliseconds later, that current drops and settles down to a much lower steady value. Why? The voltage from the wall is constant.
Something must be changing in the wire itself, the resistance.
Precisely. The resistance of that tungsten filament increases dramatically as it heats up, and this constant critical change in resistance with temperature. Well, that's the core phenomenon we need to master today. Okay, let's unpack the main idea. The fundamental principle is that when you heat a material, its resistivity, as your area, it changes. But what's truly fascinating, and what exams really focus on, is that different materials behave in completely opposite ways.
Opposite. You mean some materials increase their resistance with heat while others decrease it? That seems strange, since heating should make everything vibrate more.
Absolutely correct. And understanding why that happens is the key. Metals, like the copper in our wires, increase their resistance when they get hot. But semiconductors, like the silicon in a computer chip, they do the opposite. They actually conduct better when heated. Their resistance goes down. To really get this, let's build a strong mental image. We'll use an analogy, the crowded dance floor. This will help us track the two important microscopic factors, antimatter charge carriers, and tau, the relaxation time between collisions.
Okay, a dance floor. So the dancers are the electrons.
Exactly. The dancers, the free electrons, and the fixed obstacles on the floor, maybe some pillars or tables, are the lattice ions of the material. Let's start with scenario 1. Metals. In a metal, the dance floor is already packed. The number of dancers in is huge, and it's fixed. They're all there from the start. Now, what happens when we increase the temperature? That's like turning up the tempo of the music really fast. The fixed obstacles, the lattice ions, they start shaking and vibrating violently.
Yeah, so the dancers have a much harder time getting across the floor without bumping into a vibrating pillar.
That's it. The collisions become much more frequent. So that average time they can move freely before a collision, our relaxation time, tau, it decreases significantly.
Right, so more chaos, more collisions, smaller tau. And since resistivity is inversely proportional to tau, if tau goes down, resistivity has to go up. That's why alpha is positive for metals.
A perfect summary. Now let's think about a common confusion. If the resistance of a toaster element goes up so much when it gets hot, wouldn't the resistance just keep increasing until the current drops to almost zero and the toaster turns itself off?
That is a bit confusing. If R keeps going up, I should keep dropping.
Yeah.
But if I drops, the heating would also reduce, so it should cool down again. So does it? Does it find a balance?
You're jumping ahead to one of our key misconceptions, and you're spot on. It finds an equilibrium. But hold that thought. First, let's look at the other side of the coin with scenario 2, semiconductors. For a semiconductor like silicon, our dance floor is almost empty at the start. Most of the dancers, the electrons, are stuck to the sidelines, held tightly in covalent bonds. So the initial carrier density, N, is very low.
Okay, so not many dancers to begin with.
Right. But now when we turn up the music, increase the temperature, the thermal energy is now strong enough to break those bonds. So what happens? Suddenly, new dancers float onto the floor from the sidelines, both electrons and holes. The number of charge carriers, N, it increases exponentially. It's a massive increase.
So even if the vibrations make collisions a bit more frequent.
Exactly. The effect of having so many new dancers completely overwhelms the problem of a slightly more chaotic dance floor. The sheer increase in N more than compensates for the small decrease in tau.
So the bottleneck is different. For metals, the problem is more collisions. For semiconductors, the solution is getting more carriers, and that effect wins.
And that's the perfect way to remember it. So the mental image to hold on to is this. In copper, shaking the lattice increases scattering. In silicon, shaking the lattice increases the number of charges. That's why semiconductors have a negative alpha. Their resistivity drops with temperature. Okay, now let's bridge this to the formal insert definition. The exam wording is critical for full marks. Could you please read the formula for resistance change with temperature?
Yes. It says, the resistance R2 at the steady temperature T2 is given by the relation R2 equals R1 into 1 plus alpha into T2 minus T1, where alpha is the temperature coefficient of resistance.
Excellent. Now, that linear formula is the standard for metals and alloys, but only over a moderate temperature range. Let's just quickly walk through the physics for metals again, step by step. First, heating increases the thermal energy of the lattice ions. They vibrate more.
Which means, second, that the drifting electrons are scattered more often, more collisions.
Correct. And third, more collisions means the average time between them, the relaxation time tau, gets shorter. And fourth, we just have to remember the microscopic formula for resistivity. Rho equals m over n e squared tau.
And since rho is inversely proportional to tau, a smaller tau means a bigger rho, which confirms a positive alpha for metals. Okay, that's clear.
Right. But now for the big question. Why does that simple linear formula you read completely fail for semiconductors?
Is it because the number of carriers, n, is changing so dramatically in a semiconductor, but that formula sort of assumes n is constant?
You've hit the nail on the head. That linear approximation works for metals because n is fixed and only tau changes. But for a semiconductor, the increase in n is so huge and so fast that it follows a steep exponential curve, not a straight line. The actual relationship is something like rho is proportional to the exponential of the energy gap over kBT. This exponential nature is why semiconductors are so sensitive to temperature, making them perfect for things like digital thermometers. Hope everything is clear so far. This concept explainer is from profsam.com. All right, let's make this practical. We'll use the work example from the textbook, the nichrome heating element, to see how this formula is applied. So the problem setup is this. We have a nichrome toaster element. At room temperature, which is 27 degrees Celsius, its resistance, R1, is 75.3 ohms. We connect it to a 230-volt supply.
And when it heats up, the final current, I2, settles at 2.68 amps. And we're given alpha as 1.70 into 10 to the minus 4. We need to find the final temperature, T2.
Okay, so what's the first step?
Well, we can find the final resistance, R2, using the final current and voltage. So R2 is V divided by I2. That's 230 volts divided by 2.68 amps.
Which gives us about 85.8 ohms. So you see, just by heating up, the resistance went up by over 10 ohms. Now, for step 2, we use that formula you read earlier and rearrange it to solve for the change in temperature, delta T.
Okay, so delta T will be the change in resistance, R2 minus R1, divided by the original resistance, R1 times alpha.
Exactly. And when you plug in the numbers, you get a very large value for the change in temperature. It comes out to be approximately 820 degrees Celsius.
Wow. So the final steady temperature, T2, is the starting 27 degrees plus that 820, which is 847 degrees Celsius. That's incredibly hot.
It is. And this example really shows why a material like nichrome is used for heating elements. It's an alloy. Alloys have high resistivity to begin with, but more importantly, their alpha is relatively small and constant. This lets them get very hot and stay stable without melting. And understanding this whole topic is the critical link to our next one, which is electrical energy and power. Because the power dissipated, P equals V squared over R, depends directly on this temperature-dependent resistance. Okay, let's shift gears and talk about the silent killers, the common mistakes that cost students marks. Misconception number 1, a lot of students write this. All materials' resistivity increases with temperature.
I can see why they'd think that. Most of the examples we see are wires, which are metals. They probably just forget about semiconductors.
Exactly. For full marks, you have to explain the why. The correct idea is that it depends on the bottleneck. For metals, the bottleneck is the collision rate, so rho increases. For semiconductors, the bottleneck is carrier availability, so rho decreases. Okay, misconception number 2. This one's a bit more subtle. Superconductors are just metals with very, very low resistance.
That sounds reasonable, but I feel like it's a trick.
It is. It's an incomplete definition. The key word you must use is that superconductivity is a distinct quantum phase transition. The resistance doesn't just get very low, it becomes mathematically precisely zero. It's a totally different state of matter where electrons move with no scattering at all. And misconception number 3, the one we touched on earlier, heating a wire increases its resistance, which will cause runaway heating until the wire melts.
Right, that faulty feedback loop. But we figured it out. More heat means more R, yes. But with a fixed voltage, more R actually means less current.
Precisely. The system self-regulates. Higher R reduces the current I because I equals V over R. A lower current means less joule heating, since P equals I squared R. The power generation drops until it perfectly balances the heat lost to the surroundings. The system finds a safe, steady temperature, just like our toaster did at 847 degrees. All right, let's lock this all in with some memory anchors so you never mix these up again. Here's a simple phrase to remember. Metals heat up, their resistance goes up. Semiconductors heat up, their resistance goes down.
That's easy. And the mnemonics. MRT for metallic resistance rises with temperature, and SDT for semiconductor decreases with temperature.
Got it. Perfect. And now a physical gesture to connect it to the physics. Open your hands wide. These are the many free electrons in a metal. Now shake your hands violently. See how your fingers are more likely to collide. That's a smaller tau, higher resistant. Now make a loose fist. This is a semiconductor with very few carriers. Now shake your hands violently. See how some fingers spring free? You're creating more carriers. That's a higher end and lower resistance. The physics is right there in your hands. Okay, let's summarize the 3 key exam-safe points you absolutely must take away from this. First, in metals, resistivity increases with temperature. Why? Because increased lattice vibrations reduce the electron relaxation time, tau. Second, in semiconductors, resistivity decreases with temperature. Why? Because thermal energy increases the number of charge carriers, and this effect is dominant. And third, remember the models. For metals, we use an approximately linear relationship, that R2 equals R1 times 1 plus alpha delta T formula. For semiconductors, the dependence is a much more sensitive nonlinear exponential curve. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit profsam.com. That is PROFSAM, right? Yes, PROFSAM.com. Study hard, apply these concepts, and all the best.